This is exam 1 review, and we start with number 1, which says find the equation of the line that is perpendicular 4x plus 2y equal -4 and passes through the point 2 comma 4. Okay, so we begin with solving this equation, and we get 2y equals -4 minus 4x. Divide both sides by 2, so we get y equals -2 minus 2x. And so we see the slope of this line is m equals -2. It's just the coefficient in front of the x term. And if we want to find the slope of the other line, we need slope and point. And so the slope of this other line, called m perpendicular, is equal to, and it gives you a hint here, negative the reciprocal of the slope that gives the slope of the perpendicular line. Alright, so all that means is just take this number here and take negative the reciprocal. So negative the reciprocal, so 1 over -2, which equals 1/2. So there's the slope, and they give us the point, 2 comma 4. And once I have slope point, I can use slope point form, so y minus y1 equals m times x minus x1. And I simply plug in. So y minus 4 is equal to 1/2 times x minus 2. And I can solve this then for y, so y minus 4 is equal to 1/2 x multiplied through by the 1/2. 1/2 times -2 is a -1. And I simply add 4 to both sides, and I get y equals 1/2 x. If you add 4 to both sides, then I get plus 3. And so this is my answer. Now we can see here that the slope is 1/2, which is negative the reciprocal of -2, and if you plug in 2, and for x, you do see you get out 4. The next question talks about explaining these various things, like completing the square, the equation of a circle, and so on. So let's talk a little bit about completing a square, and we'll involve the equation of a circle with it. So first, for the equation of a circle, what do we have? So it's x minus h quantity squared plus y minus k quantity squared is equal to r squared. And of course the center is given by h comma k, and the radius is equal to, of course, r in the above formula. So let's just come up with a real quick example, and this is probably not going to be very neat because I'm making it up. So let's do x squared plus 4x plus y squared minus, let's do 2y plus 7 equals, and then let's do what? Let's do 29. Let's see what happens here. Okay, so the idea of completing a square, so we'll involve this here too. What I want to do is I want to make this thing here look like something x minus something squared plus y minus something squared equal to something else squared. And so the completing the square, the idea is you can make this into x plus or minus something squared by following the rule, add half the middle term squared. So you add half the middle term squared. And so if you follow this rule, what we can do is we have x squared plus 4x, and then half the middle term would be 2, and if we square it, it's 4, and if we add 4, we better take off 4 right next to it. And then over here, we have y plus y squared minus 2y, and half its middle term is -1, squared is +1, so plus 1. Make sure you subtract off 1 right next to it, or you'll change the equation. Plus 7 is equal to 29. And so what I get here, if you think about it, is I have these terms here, which I can collect together, and I have these terms here, which I collect together. And because of the saying, add half the middle term squared, what should happen is that this should be x plus 2 quantity squared. All right, so that's what's in green there. And then minus 4 plus, and then this turns out to be y instead of plus, it's minus because it's minus 2y, minus 1 quantity squared, and then I have minus 1 plus 7 is equal to a 29. Great. All right, so let's bring the numbers together. So I have x plus 2 quantity squared, and then I have plus y minus 1 quantity squared. I have minus 1, minus 4, minus 1, which is negative 5, plus 7, so plus 2 is equal to 29. And actually, I'm going to change this right-hand side so we can make this nice. So instead of having it equal to 29, let's just change it. And let's make it equal to, instead, 27. And you'll see here in a minute, then you'll get a nice looking radius. All right, so I subtract 2 from both sides, and you can see I'm going to get x plus 2 quantity squared plus y minus 1 quantity squared equal to 25. And so the center of my circle is given by, so my center is given by negative 2, comma 1. Right, negative because it's x minus a negative 2, and then 1 because it's y minus k, so k is 1. And then my radius, of course, this is r squared right here at 25, so r is equal to 5. And I could even draw this if I really wanted to. I go over 2, 1, 2, up 1. So here's my center at negative 2, comma 1. And I just draw a circle the best I can. And of course the radius here, r, let's just say r is equal to 5. And so that's the idea. All right, so that's completing the square and the circle. These are out of the way. Let's talk about a function, domain. Let's talk about all these. A function, domain, increasing, decreasing, local max, local min, concave up, concave down. And then finally, we can do these inflection points. Okay, so the idea of a function. Most familiar type of function, we use this functional notation, f of x equal to some formula, say x. The idea is you put something in, then you get something out. You can make this a bit more sophisticated by saying that a function is simply a rule that assigns to each element of the domain one member in the range. The crux of the matter is that if you put something in, you only get one thing out. A function can't go to two things. And so a function has a domain and a range. In general, there are three things that are going to limit our domain when we're working with formulas. So 1, you can't divide by 0. 2, if you have a square root or any even root, you have to make sure it's bigger than or equal to 0 underneath there. Otherwise, we have to deal with complex numbers. And then 3, if you're dealing with logarithmic functions or just the ln, it always has to be bigger than 0 on the inside. The range are the possible outputs. So for example, f of x equal to x squared. Nothing limits my domain because I don't have a denominator, I don't have any square roots, and I don't have any natural logs. So what I can say is that my domain is equal to all real numbers, so from minus infinity to infinity. So that's all the possible inputs. Whereas my range is going to be different because I'm squaring things. And if I'm squaring things, it's always going to be 0 or positive. So my range is actually going to go from 0 to infinity. And I can't have any negative numbers because you can't square a real number and get a negative. If you square a real number, it's always a 0 or positive. There are several other examples you can come up with formulas. Just remember domain, all possible inputs, range, all possible outputs. The next thing, how do functions change? Okay, so functions can increase, so they can go up, right, or they can go down. So they can either increase or they can decrease. If they increase and then decrease, we get what's called a local maximum. So let's call this a max. If they decrease and then increase, we get what's called a local minimum. These are also called concave down, because it's part of a frown, versus this one, which is called concave up, right, which is part of a smile. Inflection points happen when we have a change in concavity. So if you go concave down to concave up, there's some point in between here that has no concavity, and we call this point the inflection point. Concavity is relatively important to our society. If you think about it, we like to track lots of numbers like unemployment, and if unemployment's going up, it's going from here to here, there are a number of ways it can go up. It can go up like this, it can go up like this, or it could go up at sort of a constant rate, so that's supposed to be a line like that. So in general, there's sort of three ways it can go up. Now, going up on this bottom, if it's unemployment over time, this is a very bad thing. Right? It says the unemployment rate is actually accelerating. Right? Whereas this on the top, I know it's going up, so yes, that's bad, but it's actually good because maybe it'll level off and eventually start to come down. And then this one from here to here is going up at a constant rate. The next thing we want to talk about, let's see here, are the inverse functions, even functions, elementary functions, and odd functions. So let's talk about all these kind of elements because they kind of go together. So let's talk about these right here. All right, so once we have this basic understanding of functions, you put something in, you put something out, we come to this idea of elementary functions. And it's a very simple idea. It basically says most of the functions that we work with or you have worked up to now are built out of some very basic functions. One, you have what are called the power functions. Two, you have what are called the exponential functions. I guess we should write these down. So a power function looks like this. F of x is equal to x to a power, so x to the n. N can be any real number. It can be positive, it can be negative. We'll even let it be 0. And we'll also include the constant functions in here, so like 2, 3, 4, or any real number. The exponential functions, all we really need is f of x equal to e to the x. And 3, we have logarithmic functions. And it turns out all we really need for this one is the natural log function, so f of x equal to ln of x. And then number 4, we have the trigonometric functions. All right, so these involve, let's see, we have the cosine of x, the sine of x, the tan of x, right, which is really just the sine of x divided by the cosine of x. And then we have their partners over here. We have the secant of x, which remember is just 1 over the cosine of x. The cosecant of x, which is equal to 1 over sine of x. And then cotan of x, which is just 1 over tan x. So it's cosine x over sine x. So really there's just 2 trigonometric functions in some sense, cosine x and sine x. And this is what we kind of mean by the elementary functions. And all the other functions we work with can be built out of these functions by adding them, subtracting them, multiplying them, dividing them, and finally composing them. And we have a problem later where we use this composition, which is usually what students get kind of stuck on. Other types of functions we care about, there are inverse functions. So let's talk a little bit about inverse functions. The notion of a inverse function, the idea is I have a function that takes me one way. So I could have, like, let's say f of x equals, the standard example might be like e to the x. And so if I have a number here 2, it'll take 2 over here. You plug 2 into the e function, you get e squared. And you would like to have a function that takes you back to 2. And we typically call this function f inverse of x. And it turns out f inverse of x in this case is ln of x. That's one way you can define ln of x. Right? ln of x is a number that if you raise e to it, you get back what's inside here. You get back x. And so it's inverse, right? Ex takes me one way, ln takes me back. Now, of course, there's simpler examples other than this one. You could do something real simple, like instead of f of x e to the x, take it to x plus 2. All right, then it'll take 2 to 4, and then f inverse, of course, would be instead of plus 2, you do the opposite, minus 2, and it'll take 4 back to 2. But that's the idea of an inverse function. We also have these even and odd functions. So let's talk a little bit about what we mean by even functions and odd functions. So an even function, the idea is if you plug in negative x, you just get back the same thing if you had f of x. Right, so it's sort of like a football field, a goalpost on a football field. I always think, here's the standard sort of example of an even function, y equals x squared. For an odd function, you have a similar idea. You have f of negative x, but instead of positive, you put a negative sign here, and this is equal to f of x. And so instead of a goalpost, you have one going one way and the other going the opposite way. So this is y equals x cubed, which is a standard example of a odd function. Now we can do all kinds of things with these, like we can make up a function like f of x equals, let's say, absolute value of x divided by x. And we can ask this question: is it even or odd, or is it neither? It could be, most functions are neither even or odd. And the way we do this is we test it. So you can plug in f of negative x and see what happens. So f of negative x is equal to absolute value of negative x over a minus x. And then that's equal to, of course, absolute value of x. You can ignore the negative sign because absolute value makes it positive over negative x. And you see that that's not equal to the original f of x. So we know it's not even. Okay. Now, it turns out that it's actually odd. And you can see that if you put a minus sign here, then you put a minus sign here, and then a minus makes this a plus, and now it is equal to. All right, so now we can do away with that not equals, and we do get it to be equal to f of x. So it's not even, but it is odd. So f of x is odd. The next thing we want to look at are these trig identities. So let's talk a little bit about them. So for trig identities, the one that I always remember, cosine squared x plus sine squared x is equal to 1. If you choose one of these, either sine squared or cosine squared, and divide by it, so let's take like cosine squared x, divide both sides by cosine squared x, I get 1 plus tan squared x equals 1 over cosine squared x, which is secant squared x. If you divide by the other one, you get cotan squared x plus 1 is equal to cosecant squared x. So these are the standard first three identities. We also have the double angle identities. So sine of 2x is equal to 2 sine x cosine x, and cosine of 2x is equal to 2 cosine squared x minus 1. So these are called the double angle identities. And there's also these half angle identities. So we have sine squared of x and cosine squared of x. And they basically look the same. The only difference is you have a plus for this one. So cosine of 2x, all divided by 2. And instead of plus, for sine squared x, you get a minus. And like I said, these will come in handy later when we're doing integration. So those are the basic identities you're expected to know. And then finally, let's talk about the Pythagorean theorem and similar triangles. So remember the Pythagorean theorem, it's valid for right triangles. And so we have side A, B, and C. And it just says a squared plus b squared is equal to c squared. So we're going to use this theorem a lot later on in various word problems. And the same goes for the law of similar triangles, which says basically if you have two triangles, so here's one triangle. Let's make it real big here. And then I have another triangle inside it. And it doesn't have to be a right triangle, so let's just do away with that idea real fast. Let's just make it so it's clear. It does not have to be always a right triangle. So it could be any old triangle. And then you have another triangle inside it that's similar, so a triangle like this, and let's label this little a, little b, little c. And then in red, the red triangle, we'll label big A, this side big A, big B, and then big C. We know that these ratios are the same. So if you take little a, let's say, to little b, it should be equal to big A over big B. And they hold for every single one of these. Right? So if you match up the sides and take the ratios, those should be the same. We move on to number 3, which we want to find the domain of this function here. And we remember again the domain, if we're given a formula, there are only 3 things that are going to limit our domain. And this follows because of these elementary functions. There are only 4 elementary functions, and the first one we know we can't divide by 0. And the second one, if we take square roots, we need to make sure they're bigger than or equal to 0. And the third one, if we have ln functions, we have to make sure it's bigger than 0 on the inside. And so we do have a denominator. So let's switch pens here. So here's my denominator. So I need to make sure x is not equal to 0. And there's no other denominator, so that's done. And then I do have a square root, so I need to make sure x plus 1 is bigger than or equal to 0. And so this tells me x is bigger than or equal to -1. So I have 2 restraints on my domain. X can't be 0, and x has to be bigger than or equal to -1. Now I don't have any ln's, right? So those are all done. If you need to, you can make a number line. And the number line would say there's a hole at 0, because x can't be 0. And then at -1, it's everything that's bigger than it, so everything to the left. So this is all the stuff in my domain. And so I can say d is equal to include -1 to 0, don't include 0, union, don't include 0, to infinity. Now to find the range, it's a little bit harder. So if you wanted to find the range of this function, you'd have to graph it. This is not a function I would give you because I don't think its graph probably looks that great. Okay, on this one, now I want to talk about the algebra function. So I've talked a little bit about this before when we talked about the elementary functions. So the idea is that you can add, subtract, multiply, and divide to create new functions. You can also put them together in pieces. Right? So you get piecewise defined functions. And you can also, then the fifth operation here is composition, which we're doing here and here. So let's do part A first. If we want to do f of g of x, that's actually equal to, well, wherever I see a g, I'll replace it with what it's equal to. So f of the square root of x plus 2. And then that's equal to, remember, f is just a rule. It says whatever's here, whatever's right here, I put right here. And I square it and take away 1. So whatever's here, I square it and take away 1. So square it, and I get x plus 2, because the square root of x plus 2 squared is just x plus 2. And I take away 1, because that's what this says. Look at it. It says take whatever's in here, square it, and take away 1. So I squared whatever's inside here, and I took away 1, so I get x plus 1. For part B, I have g of f of x. So that's equal to, we're doing it the opposite way now, so I have g of x squared minus 1. And g, the rule for g says whatever's here, right, take the square root of it and add 2. Right, all underneath the square root sign. So this is going to be equal to, so you can see it, let's do it right here. So this is going to be equal to the square root. Whatever is here, I just write down here, so x squared minus 1, and then I add 2 to it. And so this is equal to then the square root of x squared plus 1. And you're all done. Be careful. A lot of students will try to take this square root through addition, but that is not a valid operation. Right? Square root does not go through addition or subtraction. It does go through multiplication and division. All right, so now we want to solve for x. All right, so to solve this problem, this is solving what's called an exponential equation. And all you have to do is take out your ln tool, because your ln tool will move down these exponents, and that's the real issue. So here's my equation. So what I'm going to do is I'm going to ln both sides. And if I ln both sides, ln's have the property that I can move the exponents down in front. And so what I get then is x ln of 5 equal to x plus 3 all times ln of e. And ln of e is a nice number of 1, so it's going to go away. And so I get x ln of 5 equal to x plus 3. And I want to solve this for x, so I have x ln 5. So I subtract x from both sides, so minus x is equal to 3. And I'm going to pull out the x, so I have x ln of 5 minus 1 equal to 3. Now be careful here. A lot of times students will say this is ln of 4, but you can't do that. I always tell you guys ln's a car and 5 is its passenger. And the passenger can't get out of the car unless you use one of those rules. We talked about these rules, like when you add logs, it's the same as multiplying, so a times b. If you subtract logs, it's the same as dividing ln of a minus b. Oh, sorry, a divided by b. And then if you have the ln, of course, of a to a power, p, the power can come down, so p ln of a. And that's what this is the property we're using here. So this is just ln of 5, and then take away 1. So x is just going to be equal to 3 divided by ln of 5 minus 1. And if I want to figure out what that number is approximately, I can use my calculator and do 3 divided by left parenthesis ln of 5 in parenthesis minus 1 in parenthesis for the bottom, and I get out approximately 4 point, let's do the 2 decimal places, 92. Right, so remember, when you solve an equation, you can always check your answer. I can always just plug 4.9 into for x. And if I do it on this side, I'll get some number. If I do it on this side, I'll get another number, and hopefully these numbers agree. Now, if I round it, it's just going to be approximate. It won't be exact. Okay, so here's another exponential problem. A culture of bacteria doubles every 2 hours. Assuming the growth of the bacteria is exponential, how long will it take for the culture of bacteria to triple? So on this, you want to use what's called the exponential model. And we have the amount of bacteria, so let's just say A of t is equal to the initial amount, A naught, e to the kt. So to review this real fast, remember a couple things. This is the initial. We call this the initial value. It's what you start at. And then this k has a special name. K is called the relative growth or decay rate. In this case, it's growing because it's doubling every 2 hours. So this is the relative, in this case, growth rate. T, of course, is usually time. E is a number, right? 2.718, blah, 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 the natural number. And we use this to model any exponential problem. Or we can use it to model any exponential problem. So how do we use it to model this problem? Well, I know it doubles every 2 hours. So what that means is if I plug in 2 for t, it's going to double. So I get not just a naught back, but 2 times a naught. And I can actually solve this for k because when you divide both sides by a naught, these cancel. And so I have e to the k times 2 equals 2. I want to solve for k, so I'm going to ln both sides. Because ln is this function, this tool, that will bring down exponents. So I can bring down this exponent in front. So I have k times 2. ln of e is equal to ln of 2. And of course, ln of e is 1. And so I'm just going to get k to be equal to ln of 2 all divided by 2. So this gives me some information. Now I know a of t is equal to a naught. I don't know the starting value, but now I know k, so e to the ln of 2 divided by 2 all times t in the exponent. Now it says, how long will it take for the culture of bacteria to triple? So now I'm going to pretend, so I have a naught, that t is the tripling time, so e to the ln of 2 divided by 2, and now t is not a variable anymore. I'm going to pretend t is the actual time it takes to triple. And so if t is the time it takes to triple, I don't have just a naught left. I now have 3 times a naught. And again, a naughts cancel, and I'm going to be left then with this e to the ln of 2 divided by 2, all times t in the exponent equal to 3. To bring down the exponent, I'll ln both sides. When I ln both sides, this expression right here can come down in front. And I get ln of 2 divided by 2 times t, ln of e equals ln of 3. ln of e again is 1, so it's going to drop off. And I can solve this for t. So t is going to equal, since I'm dividing by 2, to move it over, I multiply by 2. So 2 times ln of 3. Since I'm multiplying by ln of 2, to move it over, I do the inverse, the opposite. So divide by ln of 2. And so that's my time in hours. I can figure out what this is approximately with my calculator if I want to. So let's take my calculator and do 2 ln of 3 divided by ln of 2. And I get about, let's just do about 3 hours, right, to triple. Okay, number 7, I want to solve a trigonometric equation now. So this is the secant of x equals -2. So to solve this one, I don't like to work with secant, so I change it to cosine. So I have 1 over cosine of x is equal to -2. And then I can multiply both sides by cosine of x, get 1 equals -2 cosine of x. And then I can divide both sides by -2 to get cosine of x equals -1 over 2. I'm more familiar with solving this type of equation in terms of sines, cosines. And the way that this works, there's a couple tools you need to use. The first tool I'm going to use is the fact that all the trigonometric functions are positive in the first quadrant, only the sine is positive in the second, only the tan is positive in the third, and the cosine is positive in the fourth. So all students take calculus. So what this tells me is that the angle can't lie in the fourth or the first quadrant. So my thetas, whatever my angles are, have to lie in the third and the fourth. And to figure out this little angle, this reference angle from here to here, all I need to do is figure out, which angle, when I take the cosine, gives me 1/2. And again, I use another tool, which is this table. So 0, pi over 6, pi over 4, pi over 3, pi over 2. And then I have cosine of theta, and I have sine of theta. And I just have to remember the cosine of 0 is 1, so this starts off root 4, root 3, root 2, root 1, root 0, and of course they're all divided by 2, divided by 2, divided by 2, divided by 2, and divided by 2. And the sign is exactly the same, but opposite. Square root 0, square root 1, square root 2, square root 3, square root 4, divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. And now I look at this, cosine is equal to 1/2 at pi over 3. So this angle is pi over 3, and this angle down here in blue is pi over 3. These are just the reference angles. And so to find the actual angle, I have to figure out what this is here, which is just pi minus pi over 3. So pi minus pi over 3. I get a common denominator, so I get 2 pi over 3 for the first one. So I know x should be 2 pi over 3, and I can add any multiple of 2 pi, so 2 pi n. And then the other angle occurs right here, so it goes from here all the way around to right there, and so that's pi plus pi over 3. And so I find a common denominator, and this is then 4 pi over 3. And so I get and 4 pi over 3, plus again, any 2 pi, so 2 pi n. Right? N is an integer. So it's, 0, 1, 2, 3, 4, -1, -2, -3, -4, and so on. We'll end the review with number 8, which is a word problem. Whenever I do a word problem, I like to read it at least once, read through it once, and highlight what I think is important. So given a square and a circle inscribed inside of it, it is possible to determine the area outside of the square and inside the circle from the radius of the circle. So if you look at this picture, here's our circle, which is inscribed inside a square, and we're looking for this shaded region in gray, right there on all 4 sides. If the equation of the circle is given by this equation, then we want to find this area. So one strategy to solving any problem, whether it be in mathematics or any subject or even in life, is to draw a picture and then try to come up with a formula or an equation that models that picture, and then use that equation or formula somehow to solve your problem. And then you can always go back sometimes and test your answer. So this is basically 4 steps to problem solving. I did not make these up. You can read about this in George Polya's book, How to Solve It. He outlines the same 4 steps. I just make it picture, equation, solve, and test because it's PEST, which stands for pest, and students always remember it because it's like these pesty word problems. So my picture, this is already given to me, and so I usually write down what they want. So I want to find the area, in gray. That's what I'm actually looking for. And I have this formula here for the actual circle. So eventually I'm going to use that to solve for the radius. But the actual equation for the area is A equals. And to find the area in gray, the idea is let's find the area of the square and take away the area of the circle. Because if I know R, I know this length is 2R, and this width or height, if you however you want to look at it, is also 2R. Because notice, this is R, this is R, this is also R. So the length of the square is 2R, whereas this is also R, so the width is also 2R. And it's a square. Once you know the length, you know its width. A definition of a square, they have 4 equal sides. Okay, so it's easy to find the area of the square. So I want to find the area of the square and take away the area of the circle. And so this is going to equal 2R times 2R. That's the area of the square, so 4R squared. And then we take away the area of the circle. Area of a circle is pi r squared. And so all we really need to do is find this r squared, because it's r squared times 4 minus pi. And the way we're going to find r now, I'm going to solve this, and the way I'm going to solve it is I'm going to use this equation up here to figure out my r, because I know that this equation gives the circle. So let's copy it down here. So I have I have x squared minus 4x plus y squared minus 12y is equal to 9. And the way that we are going to find the radius is we're going to complete the square twice, because I know the form of a circle is x minus h quantity squared plus y minus k quantity squared equal to r squared. So if I can take this equation and write it in this form, then I can read off what r squared is. And so to complete the square, the rule is you add half the middle term squared. So this is going to be x squared minus 4x. Half of negative 4 is 2, and if you square it, it's 4. So I'm going to add 4, but take it off right next to it so I don't change the equation. Then I have plus y squared minus 12y, and I'm going to complete the square on this term here. So what is this? The middle term is negative 12. Half of negative 12 is 6. If you square it, you get 36. So I'll add 36 and make sure I take away 36 right next to it. Otherwise, the equation will change. So in all actuality, I'm just adding 0 here, and I'm just adding 0 here, so it's exactly the same equation. And because I added half the middle term squared, what should happen is that I can express these two expressions as perfect squares. So let's do that. So this is going to be x minus 2 quantity squared minus 4 plus, and then this expression can be written y minus 6 quantity squared. I have minus 36 equal to 9. And then I'm going to add 4 and add 36 to both sides, and I'm going to get x minus 2 quantity squared plus y minus 6 quantity squared equal to, and if you add 4 and 36 to both sides, you're going to get 49. And so now I know that my r squared is equal to whatever term I have on the right, because I have it, x minus my h is 2 squared plus y minus k squared is equal to, this must be r squared, and so r squared is equal to 49. Therefore, my area is equal to, that gray region is equal to, r squared times 4 minus pi, so 49 times 4 minus pi. And then this would be units squared. And so that's my answer. Now to test this, I think the best way to probably test this type of problem is actually to build it. You can actually take a piece of paper, you can cut out a square, and it's 2r, so length 14. Length 14, it could be in inches, it could be in centimeters, it could be whatever. You could take a compass and find the center and create the circle. And you can figure out the areas of the sides here, what they actually are. Some ingenuity might have to go into this. Sometimes to find the areas of things, what they do in chemistry is they can measure the weights of these things. So if you take the weight of these little shaded regions, you can take it on some sort of balance that can tell you the weight of something that's really light. And then you can actually divide it by the weight of the whole square. So what you can do is take the weight of these little 4 regions. You can cut them out with scissors. I'm going to draw them here, but you can cut them out. And you could take this ratio. So you take this ratio, and so this is me sort of thinking. So you take the weight of these little pieces divided by the weight of that square, and that's going to equal the area of those little pieces divided by the area of that square. These you know. These you know. You find from the balance. This you know, 14 times 14. And this is your unknown, so you should be able to solve for it. I don't actually think you're going to go home and do this, but it's kind of interesting to think about how can you test to see if your answer is correct.